Hi everybody, welcome back to the ABC networking community. As you can see, my name is Marius. Today I'll be doing the ABCs of networking video 4. I'm going to be talking a little bit about half duplex versus full duplex. In my previous video 3, I actually spoke about a hub versus a switch. And this actually leads on to that a little bit, but that video became a little bit long, so I thought I'll just split the two up. So this is an extension of video 3, effectively. But I'm not really going to go too much into the hub versus switch and so forth discussion. It's more a base of half duplex versus full duplex. What does it mean? Is it relevant today? Hell yeah, it is, of course. Otherwise, I mean, it's still relevant. I think if you look at networking going forward, I'll talk a little bit about that. I just want to mention tokenry, interesting stuff. I want to go into Ethernet, the VHS versus beta discussion type thing. Then I'll see in Ethernet, how they evolved Ethernet over the time. Right, or over time to today. Okay, so effectively, just to jump to the next page. All right, so like I said, what we want to discuss today is half duplex versus full duplex. And that should be quite an interesting discussion, I believe. Okay, so let me just select the pen here quickly, then we can start. So half duplex, oh that's so boring, isn't it? Okay, let's change color. Okay, half duplex versus full duplex, and let's just make it a bit of a proper line there. Okay, so why do I want to talk about this? Like I keep on saying to you, I always come back to the OSI model. Yep, OSI model. And I always keep on saying that networking is not something that we invented from scratch. It's a bunch of conditions that came together that created some opportunities, but also as we evolved those opportunities created some challenges. And as those challenges were faced, people had to make options or had options to solve those challenges. And they looked at different criteria to fix it. And one of those things is half duplex versus full duplex. I'm going to go back into 1967, where they basically created the first network, and they took two devices and connected them together. So when I talk about half duplex versus full duplex, also what I would like to also just mention at the moment is, you'll see me, I'm actually going to talk about this as point to point. You might have seen this around. Point to multi-point. If you've ever tried to do something like a CCIE, this is really important. OSPF, right, handles it differently. All the type of network training, you would have seen something about this as well. Well, it comes down to the same thing. It's how you address people. This also leads into something else. It is the types of discussions we can have. It all ties together. Half duplex, full duplex, point to point, point to multi-point, or something like, from a discussion point of view, when I actually have unicast type traffic, or if I have multicast / broadcast type traffic. All right, this would be like a point to point traffic, this would be like a point to multi-point traffic, this would be half duplex potentially, and this would be full duplex. But there's a linear line between them, yeah? But what you'll see as I move across, so you'll see there's similar characteristics as we go forward. And that's why I say it's all pretty much tied together. Right, now let's forget about networking for a while. When I have a discussion to you as an audience, right, my audience, I have no idea who's watching this video. Yeah, I think it could be quite scary. But anyway, so from that perspective, I have no idea who's sitting on the other end. So I have to make the assumption that I have people listening to me, right? And that's a broadcast type message that I'm sending. I can keep on talking all day long. In the background, you could be having a conversation to somebody else, and that doesn't bother me the least. All right. So what I mean by that is you're not disrupting me while I'm having this conversation, even if this was live, right? This is a live stream, because you had no communication back to me. But let's just say you had communication back to me right now, and we had an audience of a couple of 100 people or 10 people or 5 people, it doesn't matter. Right, if you actually could talk back to me, if you think about a good communication, if you watch CNN and all those type of broadcast TV stations, you'll see when they actually have a reporter in a remote location far away from UK, and that guy actually is on a video phone, all right, or having a conversation, you'll always see a bit of lag in between. Now that's true for networking as well. There's some type of lag in between from where the message starts to where the message arrives. There is a time period, right? That's called delay. Okay, so what does that have to do with half duplex, full duplex? Bear with me for a couple of minutes here. I'm going to show you. Okay, so that's delay. Right, and in some cases, because we're using satellite phones, they most probably, that delay could be anything but 300 to about 500 milliseconds in time. Okay, so as the message is traveling through time, right, goes to the other side, at the same time, you'll sometimes see the reporters have it down quite well at the moment. They actually wait, you'll see that they actually have a bit of time before they start to speak. And there's always a bit of a buffer in between. And then this reporter will sit there, and they will most probably have keywords that they send to each other. All right, in the discussion. And when that message runs out, this person starts to talk, because otherwise what you find is, while this guy's information is coming through to the station, this guy is starting to send information back or having a conversation, there's a bit of a clash in between. And you have to restart from scratch. And then it's normally the case, oh no, you go first, oh no, you go first, okay, okay, you can go now, and they keep on clashing with each other. Right, so because of all of that, that's nothing different to what happens on networks. So having a point-to-point type conversation, one-on-one conversation, right, over a short distance, makes it quite easy to communicate. Right, so you can see how this can be a bit of a challenge, because we're sharing the similar infrastructure. So they had the same issue there. As long as they had one cable, two devices, there was still an opportunity where this guy was sending data, that this guy was sending data at the same time, and what we basically have is a clash of electricity in between and a whole mangled up data pattern coming through to the other side. And what would have to happen is that there would have to be a time period that they would sit and wait right before they resend the traffic again. Now if it's point to point, what's the chance of that happening? One-on-one. Right, but if I had an audience of, let's say, 15 people now, and while I'm talking and there's a bit of delay in between, there's always a bit of delay, right? It's normal networking. And somebody started speaking on the other side and they want to ask a question, because I actually kept quiet for a while, right? That person sees an opportunity to start speaking, but I'm not finished speaking. So as I start speaking and you speak, I have a bit of a clash, and we have that thing of communication, go, okay, you go, me go, and so forth. Okay, so that can happen with point-to-point, but it could also happen with point-to multi-point. So if I, and there's a better chance of this happening with point-to multi-point. So if I add another device here, and I could actually say, well, the evolution of networking led me to hubs, right, with a flat type network. So we actually had an infrastructure where we actually had devices connected now, all right, let's say to a hub. Even though physically this is exactly what it looks like, logically it looks something very different. It looks like this. Logically it's a flat line, right, with a bunch of devices on it. Okay, because the hub basically just extends the information, just keeps on sending it. There's no logic there. Okay, so if this guy starts to speak, the traffic will go there, there, and there, irrespective. And at the same time, if this guy spoke, we basically would have clashes somewhere along the line, right? And everybody would have to re-speak again, or resend the traffic. Re-speak. How awesome is that? Okay, anyway, so from that perspective, even if I turn this into a switch, right, I think I can actually just drop it out like this. Even if I turn this into a switch, right, what would happen is, let me just quickly select my lines again. So that's a switch now. If I had half duplex, right, flat network, basically I would have exactly the same communication line as this. Even though this could be point to point, but basically if I turn it into half duplex, what I am saying is that traffic will flow everywhere. So there has to be a set of rules that they had to come up with. Okay, so I just really want to jump a little bit into token ring as well, because there was two main streams of transferring data many, many years ago, right? And I'm going to say on the one side is token ring, and on the other side we'll talk about Ethernet. Even though it wasn't known as Ethernet in the start, it was a different technology. Okay, anyway, so token ring itself, right? So from a token ring point of view, what they said was, well, what if we actually had 4 devices? And what we said was, whoever holds the pen, if I had a pen and I had 10 people or 5 people around the room, and whoever holds the pen talks. If you don't have the pen, you cannot talk. Okay, it's like a microphone. Let's say microphone is a better idea. Microphone. Okay, so the microphone goes around the room. Okay, some people will try and talk without a microphone, but we just ignore them. Okay, they're not important. So what happens is these devices are actually interconnected with each other. All right, and whoever holds the token, so the token would go through the network. And if somebody has a message, he holds onto the token, sends the traffic through, he gets it, this guy gets it, this guy gets it, and gets it back again, and he releases the token, and the token flies again, and this guy gets a token. So only one person can talk at any given time. There's a small delay in that, but the fact is that if you have traffic controlled like a little policeman, that makes a lot of sense because you could actually get quite a good throughput. On the other side with the Ethernet, what they had was, they said, well, that doesn't work because I've got a flat network. All right, so I've got 1, 2, 3, 4 devices, and as this guy sends traffic, it's a flat network, it goes absolutely everywhere. Okay, so collisions could happen. So instead of saying, well, no collisions, what they are saying is, well, in the case of collisions, if we all use the same algorithm, right, all the times, to come up with a resend option, if this guy sends the traffic, he sends the traffic at the same time, there's a collision in the middle, and we actually use the same timer, let's call it 1 second for now. No, a second is really long, but let's call it 1 second for now to resend. By the time this guy receives broken packet, he takes 1 second and resends again, and resends. What's the chance of them resending at the same time? Pretty damn good. Okay, so what you're seeing is that they actually had to come up with a random algorithm. So I want you to come up with a random number of 1.4872 seconds. And this guy runs a random algorithm and comes up with 0.74218 seconds and sends. So he gets this message through before this guy can get the message through. Okay, so that needed to be a random. So they had to come up with a set of rules back to the OSI model, OSI model. Okay, and what they came up with, the set of rules, was something called carrier sense, multiple access with collision detection. Simple. So what this guy does is, as soon as you multiple access, I've mentioned this a couple of times in the previous videos, but if you have multiple access, yes, I have multiple access on the same piece of communication mechanism. There it is, right? And they're all connected with nothing in between controlling it. So that's multiple access, yeah? You have to carrier sense. Like I had the conversation, that reporter, they might have keywords that they use, right, between them, and they must probably train this a couple of times, so that the other side knows that the last word that came in was X. Okay, so that's carrier sensing. It's some type of intelligence waiting for things to happen, making sure that there's no traffic on this link, right, based on algorithms. And then should there be a collision somewhere, collision detection, there should be an actual random algorithm to resend the traffic. Get it back. Okay, so that's what they did with Ether. All right, so that was the initial response. Now this was true for point to point and point to multi. I should say to the multi-point. Yeah. But then they came out with something called a switch. All right, and the switch gave them opportunities, because if you think about this, how can we fix this? Well, the way you fix this, number one, is not just to have one piece of copper. Okay, I have one piece of copper here with coaxial cable, or had, let's say those days. So the way we can do the actual Ethernet is, and we know what happened to the whole token ring thing. It was always interesting for me when we actually had token ring competing with Ethernet. Token ring always came close to the reported numbers. So if they had like a 248 whatever meg throughput potential, right, they actually got to that number quite close to it. They could get to 90-95% of it. Right. Please don't shoot me for that, but that's effectively, you could get quite close, depending on the infrastructure that you built. On the other side, if you actually had Ethernet, right, Ethernet with half duplex, because you had to carrier sense, it takes time, that's delay, right? Because you have multiple access, the more you have on there, that creates more delay, right? With collision detection, that's also delay. You can't just send packet one after the other, right? It's like a one-lane highway. So to start with that is, I have device and device with one lane here, one lane highway. This direction equals true and this direction equals true, right? So there's no ways this guy could be sending at 10 meg and this guy could be receiving and sending back at 10 meg. So you can start to see what happening. There's no ways he could say, well, from a 10 meg point of view, I'm going to send 5 megs this way and exactly time it so that this guy can send 5 megs as well. Right, so what they started seeing is, because I had to first carrier sense, that was delay. I had to see the more devices, the more delay I created, and of course collision, if there was collision, because this was best effort. Right, tried to send a packet through, and based on algorithms, I hope for the best. Right, so this was always about 20 to 30% of potential. So I got, let's say, if I was lucky, 3 to 4 meg throughput on a 10 meg line. yeah, because of all of this, you know, carrier sensing and multiple access and collision detection. But what if I did this? What if I took a device? These guys must have sat back and looked at this and said, well, how do we solve this problem? Well, the problem in this whole algorithm, that whole thing there, the problem, right, is not carrier sensing. How do we carrier sense something better? It's difficult, man, because the more devices you add, you have to be really synced up with algorithms and so forth. It's very difficult to change that. Collision detect, well, you have no choice, because if you don't carrier sense proper and you have multiple access, you will have collision, so we can't change anything there. But what about if we made this multiple access, single access? Yeah. What if, how do you do that? Well, I've got a piece of copper. What if I actually had two pieces of copper? There's a piece of copper, and I'm going to put another piece of copper in there, a second piece of copper. And I have an algorithm between these two. I actually come up with an agreement between them, and I say to them, this is pin 1, all right, going to, don't shoot me, I'm using the wrong pins here. I know which the ones they are, but don't shoot me. Going to pin 2, and let's say this is pin 1 going to pin 2. So somewhere in this cable, right, what I am saying is, I'm not talking about cables right now, but I'm always going to say to this guy, you always send on 1. And I'll say the same thing to him, you always send on 1. Right, you never send on 2. You only receive. Right, so that's transmit, and this is receive on 1, and you transmit and receive on 2. Okay, so I shouldn't say send there, that's actually completely wrong. That TX transmit on 1 and RX on 2. That's a very simple rule to come up with, right? But it's pretty ingenious, it's bloody clever, man. Think about this, because if I'm sending on 1 and I keep on sending over there, and this guy can never send on 1, there could never be a collision in theory. There can be broken packets, forget about attenuation and stuff like that, but effectively there can never be a collision. It's a one-lane highway. So what they've done is, oh, this is pretty cool, is they've created a highway with a barrier line, as a matter of fact, a solid line in here. Not a barrier line, a solid line. That's their highway. And traffic will only flow on the one direction. And unlike people, devices will not start sending traffic across there, okay, if it's set up this way. So what they said was, they said, well, from a half duplex where we share a common infrastructure, we now have something called full duplex. Double. All right. So if this guy is sending, is there multiple access on this? No. Well, if there's no multiple access, why do I have to carrier sense? Duh, don't have to. Right? And if there's no other people sending on that link, how can there be a collision? No. It can't. Oh, so that's pretty cool. So it means that this rule is gone, which created a lot of delay. So if I'm the only guy on that link, and I have the potential to send 10 meg, why can't I send 10 meg? Yes, you can. Okay, at the same time, if this guy wants to respond, what does he do? He responds over this 1. He's going to use 1. And you use 1. How cool is that? Okay, so effectively what we can nowadays, we can get 10 meg one way and 10 meg the other way, which means we get 20 throughput if they both spoke at exactly nice condition. So this is pretty cool. I can get over a 10 megabyte line, I can get 20. Okay, so this is very interesting. Unidirectional, and this is bidirectional. Be very careful. Bidirectional, sorry. Be very careful when you look at numbers from vendors, what they are saying. Is it unidirectional or bidirectional, especially on switches? Okay, so this is all so cool. Okay, this is really cool, but there's a challenge with this. Okay, let's throw this into a challenge, because what we have to think about is, if we go just next slide there, let's just say what I am going to do is I want to have a full duplex concept, but on a hub. So work with me for 1 second here. What does a hub look like? A hub's got a piece of copper in the middle here, right, terminating and terminating, and effectively connecting to a device, another device, and another device. please work with me here. So even if I had a second cable going in here, and a second cable going in there, and a second cable going in there, and a second cable going in here, what would happen? Okay, maybe I can change the colors. This will actually work quite cool. Wait, give me 1 second. Give me 1 second. Okay, if you may, give me 1 second. Yeah, how cool is that? Okay, so even if we did this, I'm going to create, so we say we transmit TX on 1. I haven't done this before, so I'm going to try and work it out in my head as we do this. And we're going to RX on 2. So what if I created an RX link here, all right? Let's call this RX. And we, sorry, TX, and we actually had an RX here, receive. Okay, and we actually took a device. I'm going to add a device to this now, a PC. And what I did is I actually had bi-directional, so I would create, let's say, 2 cables. Let's say I had this opportunity. Bear with me for a second, and I would create a device connected to there, and at the same time I would also connect this guy over there. How cool is that? Okay, work with me. We might be developing a new device here. Okay, so second one. Give me 1 second, and we say, oh, wait a moment. It's a bit of a challenge here. Okay, because what I can't do is, if I transmit over there, and this guy's transmitting, I have bi-directional. I'm doing this for a purpose, by the way. So do we connect that over here then? We'll have to, don't we? We've got no choice. Because this will have to send and this will have to, so this will almost have to be a funny thing here. It'll have to switch between the two, whether it's receiving or sending. Okay. So that can't work with a hub. So with a hub, we would basically, the traffic comes through there, and we would have to, I think we just build a new device, man. Okay, because if this guy sends, think about it, the packet flow, let's do the packet flow, it fires out, comes through. This guy can't compete with it, right? So it basically goes into a receive and goes across. That's pretty cool. And the same thing over there. Say if I do this as a direction, right? And this guy goes across, sends in, gets there, and goes into receive. Okay, that's pretty cool if you have a 2-port hub. Oh, by the way, this is also known as a crossover cable. Okay. So we didn't invent anything new. What we have is we've got a PC sitting over here, we've got a PC sitting over there, and what we've done is we've actually crossed the cable. Okay, so as it comes out as a transmit, at some point we're going to cross it over into a receive. And the same thing happens over here. The transfer goes out there, and at some point it crosses over into a receive. It's a crossover cable. Okay, so why I'm laughing at this point is, of course, this is great. It's a very expensive way to connect to devices is with the crossover cable. Anyway, so from a hub point of view, the challenge that we have is, what if we added the device here? In theory, what you would have to do is you'd have to create all of this again for a second time, because think about it. If this guy wants to talk to that guy, you should have a transmit and a receive pair that he would have to connect to. And if you add another device, you would have to do that again, because he would have a transmit and receive for him, but at the same time he would have to have a transmit, right, and a receive for this guy, because he could be, you want to create a point-to-point environment. So this is all becoming really messy and really dirty. And remember, this is for a device that has no logic. Okay, so let's move further. Okay, so what they did is they obviously had the same challenges. Okay, let's get into the next slide there. And what they did is they actually created something called a switch. Okay, so what the switch did was very clever. The switch actually had a control plane. It actually had control for those guys doing what's named SDN. This is where you divorce the control plane from the data plane. Yeah. Data plane is connectivity, control plane is logic, understand. So, what happened there? Okay, that's better. Okay, in this control plane, effectively what a switch will do, I'm going to go through really quickly what a switch does. You have a PC connected to a PC connected to a PC. Yep, they also have MAC addressing. But what you would do very importantly is you would actually have a transmit in there, a transmit and a transmit. At the same time, you would have a receive and a receive. Very quickly, I'm just talking about basic switching. So what happens is if a packet enters, flow with me here, work with me. The packet goes from A, let's say this is B and C. Let's say the packet needs to go to C. It's a unidirectional packet. I want to get full duplex. Packet flows out into the switch. What the switch will do is it will pre-position the packet, will send it everywhere. So the packet ends up over there and over there. Right, but also goes into the control plane. The control plane says, based on the MAC address table and some rules and regulations, VLANs and everything else, all right, the control plane will say, okay, everything but, let's say this is port 1, 2, and 3. The packet is from A to C, right? So fires out, the control plane says all ports except C drop. Okay, so all the ports will drop the actual packet except for C, and C will forward the packet, will release the packet. Okay, that's one way of switching. There's another way with close switching where we can actually talk about that as well, but I don't want to get too deep into this. But you can see what happened now with full duplex versus half duplex, because with full duplex what you have is this guy could be sending at 10 megs, this guy could be sending at 10 megs, and he could be sending at 10 megs all at the same time. Now if we look at switching today, they talk about the backplane. Right, okay, and the backplane speed in reality, and the backplane speed is 1 terabyte, 1 terabyte potential. Okay, so what they're saying is that you could actually have a full duplex environment up to 1 terabyte. It doesn't matter how many ports you have, right? You could have 100 ports on this switch, right, all sending 1 terabyte, but if the backplane is only 1 terabyte, it'll be 1 terabyte. That'll be pretty cool, 100 terabyte ports. But anyway, the backplane determines the amount of full duplex potential you can have before it starts to throttle back the actual devices. But the throttling back will actually happen on the ports, right? Will actually start throttling back, so it will not create congestion and collision. Because what you do have is you have a true, the switch, think about it, switches, right, will actually create a connection, a logical connection between these two devices for that flow of traffic. Okay, so it creates a point-to-point environment every single time. If A spoke to C, if at the same time A spoke to B, it will also create a flow there as well through the switch. The switch would control those as point-to-point links. Okay, so the one thing I've seen in the older days, and don't make a mistake, I've even seen this recently, is what somebody says, well, okay, I only have certain ports, I only have 4 ports available on the switch. So he used to have another device here, right, and this used to be, let's say, D, but they need to put E in there as well. So what they would do is they would actually connect a hub in here, and then connect D over there and E. Okay, and a lot of times what happened is people never changed that. So to the switch, what the switch would see, wait a moment, okay, I've got a full duplex environment. I am going to be sending over one link and I'll be receiving over the other. This guy says, hey man, this is half duplex. I'm going to carrier sense, multiple access, collision detect. And he's going to start sending traffic at intervals. But this guy is sending traffic all the time. He just keeps on boom, 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 because he's allowed to. It's full duplex. And a half duplex device suddenly doesn't know what to do with this. So what you start seeing is a lot of collisions on this infrastructure. And if you actually do the display interfaces commands, you'll see some of the counters there. It's well-known counters will start to errors increase quite quickly, dramatically. So you must be saying to yourself, well, come on, man, this is 2016 or whatever the case may be. This doesn't happen anymore. You'll be absolutely surprised. I saw a network in South Africa taken down for 2 days, 2 solid days, because of a duplex mismatch. Right, it was so well hidden away that nobody picked it up. Okay, there was a duplex mismatch between the actual 2 devices, and that created a lot of flood and noise on the actual network, and that just killed everything right on that infrastructure. In that case, it wasn't a hub. I don't want to go into details because that was vendor specific, but there was an actual really enhanced device that was sitting over here that was just set up absolutely improperly. And you must be saying to yourself, so who still uses half duplex if you have full duplex? Well, if you think from a Wi-Fi point of view, right, how does that work? It's contention. People contend for the AP. I'm not going to go into details there, but in theory, not in theory, in practice, what you have is you've got contention on the Wi-Fi infrastructure. So that's why you'll see with the Wi-Fi infrastructure, the more people you add to this AP, all right, the more contention you get, the more collision you get, and of course the more drops you get and resend you get, right? And then of course the throughput drops through. There are ways that they of course do it, make it better, because they create multiple channels of it, right? But they can't have a channel per device. Right, so what you effectively end up with is you end up with a half duplex infrastructure over Wi-Fi. So is it relevant? I really think so. Okay, so you can see how I try to draw the analogies between point-to-point type traffic, because point-to-point traffic is always easier, right? And what you also see is you have point-to, multi-point. The behavior, great example in OSPF, I'll get there, don't worry. Great behavior of how you control traffic in a point-to-multi-point is very different. Right, and the problem is when you try and mix one with the other. If you say to both devices, you are now point to point going to point to point. This is fine because a set of rules apply. I am talking to you, all right, as a person, and you talk to me back, all right? Which is not happening, but I mean, if you have a point to multi-point environment, all right, connected to a point to point, this guy is going to feel he's got a point-to-point type connectivity and discussion going on, and he's going to flood the point-to-multi-point environment. The scary thing is if people think they are point-to-point in a point-to-multi-point environment. The scary thing is if people think that they're in a full duplex environment or devices, and they're actually in a half duplex environment. Because they're not checking anymore, they're not doing carrier sensing anymore, they're not doing collision detection, they just push the traffic. And what you do see is you see a really big influx of CRC. Cyclical redundancy checks, right? Because the packs will start to collide and fires through, and somewhere the packet will have to be dropped because it's broken. Okay, and those are the errors I spoke about. Okay, so I hope you find value in this video. I just wanted to quickly discuss, the full duplex versus the half duplex. As we move forward, you can see one of the things that the actual switch is doing at the moment. So I believe that what I want to discuss next with you, right, in video 5, I believe would be the right thing to do, is maybe to then look into the switch. Now, we now know one of the benefits of the switch. It gives you a full duplex infrastructure of potential, right? That's one of the things it will give you. One of the other things it will give you, of course, is, can you think of anything? Right? Not just full duplex itself, but basically the throughput goes up, but it also gives you the logic, which means I can start to create things like VLANs. Because what you will see is, once we had a full duplex environment, I'm going to show you in the next video, is once we had one switch, we had a couple of devices connected to it, life was really good. But what do we do if things are good in networking? We abuse it to the point that it breaks. So we started adding a whole lot of switches into this, right? And even if you actually had unicast traffic, that was now segmented, we spoke about that in video 3, right? We had unicast traffic, broadcast traffic still went absolutely everywhere. And there's got to be a breaking point of how far you can stretch this. And then something else happened at the same time. Well, what if that link breaks? Networking became more important now as well. What if we put a second link in here? And the next thing that comes up that I want to talk about, of course, after VLANs, is going to be spanning tree protocol, STP. Okay, once again, and I think those are the things I want to drive around a little bit, from a layer 2. There's a lot of things to talk about in layer 2, yeah. Okay. So once we have this under the knee and we understand all of this, right, I'll talk about spanning tree, how that works, the root bridges and so forth. That'll most probably be the video after this. I first want to talk about the actual logic of the VLAN, how we solve the broadcast issue. Right, and then of course we created redundancy, and that created another issue called, broadcast storms. Right, and loops, sorry, small loops. I'm thinking about broadcast storms, yeah. Okay, so it created an actual loop. And once you have a loop in layer 2, that's a nightmare, and that still happens today, everywhere. Okay, so we'll talk about spanning tree, how spanning tree solved that. And once we've gone through that, we'll most probably start to move into the routing space, my favorite space to be. Okay, and with that, I just want to thank you for your time. I really appreciate that you've watched this video this far, and I look forward to seeing you in video 5. Cheers, guys. Bye-bye.